The star is steady on screen. Not steady in reality, never perfectly steady, but steady enough that we can pretend. Then a dark circle approaches. An exoplanet, HD 189733b. It slides across the face of its star, and for a moment, the universe offers a thin, almost impossible gift, a rim. A sliver of atmosphere backlit by starlight. The only edge we can touch from here. On a monitor, that edge is not an image. It's a line, a spectrum. Light broken into colors so fine they feel like a confession, and then quiet. A feature that used to stand out fades toward the noise floor like a voice that stopped mid-sentence. The title promises it plainly. Eclipse rim on HD 189733b went quiet. Telluric contamination, the full story. The hook isn't wonder, it's credibility. Was the exoplanet's atmosphere changing, or did our own sky drown it out? This is the first tension we have to carry without flinching: signal versus artifact. Planet atmosphere versus contamination. Detection versus interpretation. Because at the rim, especially at the rim, everything is small. HD 189733. B is not a gentle world. It's a hot Jupiter large, close to its star, bathed in relentless radiation. We've been looking at it for a long time because it's bright enough, close enough, and cooperative enough by exoplanet standards to be studied. Not because it's habitable, not because it's a place to live, but because it's a place to learn how to read atmospheres without lying to ourselves. And read is the right word. We don't watch weather, we don't take samples, we infer, we interpret. We pull meaning out of faint starlight, and then we argue with our own conclusions. At the center of the mystery is the word rim. At the moments when the planet begins to cross the star or finishes crossing it, we're seeing something different than at mid-event. The geometry changes. The light path changes. A thin slice of the exoplanet's atmosphere becomes the main actor for a few brief beats. Ingress and egress. Those edge moments sample different paths through the atmosphere than the deeper, steadier middle. If there's structure in that atmosphere, cloud decks hazes. Temperature layers, those details can show up differently at the edge. So when something went quiet, it matters where it went quiet. If it fades at the rim, it might not be the same story as a feature that fades everywhere. Here's what quiet means. In the language of measurement, a feature looks muted, flattened, less distinct, closer to a straight line than it used to be. In an exoplanet atmosphere spectrum, that muting can have more than one cause, and the causes don't announce themselves. One possibility is the planet itself. A muted feature can indicate that the atmosphere is hiding its own chemistry behind clouds or hazes high-altitude particles that scatter light and wash out absorption signatures. When that happens, the spectrum can lose its sharpness. Not because the gases vanish, but because we can't see down to where the gases imprint strongly. Another possibility is that the atmosphere's structure changes with time. Wind-shifting heat, moving condensates, forming and dispersing. On a world as intensely heated as HD 189733b, it's plausible that the limb, the edge we sample, could vary from one observation to the next. Not guaranteed, not proven, but physically plausible. And then there is the third possibility, quieter than the planet and closer than the star, our own air. Telluric contamination. Earth's atmosphere leaving its own fingerprints on the same starlight we're trying to interpret. The title doesn't treat it as a footnote. It puts it in the center. Because if the rim on HD 189733b went quiet, we have to ask whether it was the exoplanet's atmosphere that changed, or whether Earth's atmosphere changed in a way that made the exoplanet harder to hear. This is the part that feels almost unfair. We are searching for atmospheres while living inside one. The rim is where the signal is smallest. The sliver of atmosphere is thin. The effect on starlight is subtle, and any small mismatch in what we subtract or correct can loom large in the final result. A tiny error at the rim can look like a profound change in the planet. So our first job is not to romanticize the mystery. It's to define it. What exactly went quiet? Was it a specific dip in the spectrum? One wavelength region that used to show a recognizable imprint and now does not? Or was it a general flattening and overall muting that hints at haze or a different thermal structure? The outline keeps us honest here. We do not get to claim a specific gas or a specific line. We only have the shape of the tension feature versus flatness, persistence versus disappearance. And that's enough. Because the story isn't about a single molecule. It's about the inference chain. It's about how easily we can mistake the act of measurement for the behavior of an exoplanet atmosphere. There's a temptation when a signal disappears to treat it like a plot twist, like the planet is playing games. But the more honest framing is colder. The rim is a place where our method is most vulnerable. And vulnerability is not a failure. It's a map of where we have to look hardest. So we hold two ideas at once without letting either become a crutch. We have a well-studied exoplanet with an atmosphere. A rim feature going quiet could be the atmosphere's structure clouds or hazes muting what we once saw. Or it could be time variability on the planet. And threaded through all of it is the confounder that never takes a day off Telluric contamination. The title's promise. The full story is really a promise about discipline, about refusing to let a single curve on a graph become a claim that outruns the evidence, about asking the one question that keeps science from turning into wishful narration: could this be us? Because the moment we say went quiet, we're implying a change. And change demands an explanation that survives cross-examination. That cross-examination begins with how the data are made. At all, how eclipse and transit spectroscopy turn starlight into a story about an exoplanet atmosphere. If the rim is the faintest whisper, we need to know exactly how we're listening, what we're subtracting, and what could silence it by accident. So we follow the light backward from the quiet line on a screen to the messy real sky it came through, and we ask step by step what it would take for a planet to go quiet, and what it would take for us to think it did. The room is dark enough that the monitors feel like windows. Not into space, into the act of measurement. A star, a planet, and a stack of numbers pretending to be simple. The first thing to admit before we say anything confident about an exoplanet atmosphere is that the planet is not the brightest thing in the scene. The star is. The planet is a small subtraction, and the atmosphere is a smaller subtraction still. Eclipse and transit spectroscopy lives in that hierarchy, a big signal, a smaller dip, and then a faint pattern inside the dip. So how we know begins with a ritual that looks almost too mundane for the stakes. We watch the star when nothing is happening out of event. We watch it again as HD 189733b moves into the geometry that matters during the event. We split the light into colors because the atmosphere doesn't block all colors equally. And then we compare. In the simplest terms, eclipse/transit spectroscopy is a difference measurement spectrum in event versus spectrum out of event, looking for wavelength-dependent changes that can be traced to an exoplanet atmosphere. That's the clean version. The version you can explain in one breath. But the title isn't clean. Eclipse rim on HD 189733b went quiet. Telluric contamination, the full story. The full story is that this difference measurement sits on top of other differences. Changes in the sky above our telescope, changes in the instrument, changes in the star itself. And those differences don't politely label themselves. So we have to be precise about the chain. At the moment of ingress or egress, the rim, the planet, is only partly involved. The atmospheric sliver we want is the smallest. The star is the same bright floodlight it always is. And the measurement we're trying to extract can be close to the boundary between signal and noise. That's exactly where Went Quiet becomes both a clue and a trap. Here's the heart of the method in plain language. We aren't detecting the atmosphere directly. We're detecting what the atmosphere does to light passing through, or what changes when the planet hides behind the star. The atmosphere is effectively a filter, but we can't hold that filter in our hands. We only see its effect as a slight color-dependent change. And there's a second filter we can't remove, because we live inside it, Earth's atmosphere. Telluric contamination is not a metaphor, it's literal. Earth's air absorbs light at specific wavelengths, leaving patterns, lines that can overlap the same wavelengths we use to study an exoplanet atmosphere. And the cruel part is that Earth's atmospheric imprint is not constant. Telluric absorption varies with humidity, temperature, and air mass, how much atmosphere the starlight passes through on its way to the detector. That means telluric lines can deepen or weaken over the course of a night. They can shift in their apparent strength in ways that correlate with the observing conditions, not with D189733b. So the difference measurement is haunted. Because if Earth's imprint changes between out-of-event and in-event, it can masquerade as a planetary signal, or erase one. This is the central tension pair in the method signal versus artifact. Planet-atmosphere versus contamination. And it's why the rim is so dangerous. The smaller the planetary contribution, the easier it is for a telluric mismatch to look like a planetary mystery. The calibration step is where we try to fight that haunting. We model Earth's atmospheric absorption. We track the observing conditions. We correct. We subtract. We attempt to recover the star's spectrum as if Earth weren't in the way. But a correction is not a guarantee. It's a wager. If the telluric correction is imperfect, it can suppress or fabricate features, making a real rim signature appear to go quiet, or making a quiet rim appear to contain a feature that was never there. This is exactly the kind of subtle, devastating failure mode that title points at the exoplanet doesn't have to change for the story to change. And then there's the instrument itself. Even if Earth's atmosphere were perfectly modeled, we still have to trust the stability of the spectroscopic measurement. The detector responds. The wavelength solution holds. The calibration doesn't drift, but instruments live in the real world. Thermal changes, subtle shifts, small nonlinearities. Outside this how we know section, we won't unpack the machinery. Here, we have to acknowledge its existence as a confounder. The data we interpret are the product of both astrophysics and calibration choices. We're not just measuring the exoplanet atmosphere. We're measuring the entire system sky telescope detector and then trying to subtract everything that isn't HD 189733b. This is where good teams become cautious. They don't trust one pipeline. They don't trust one night. They don't trust one narrative. The outline gives us the correct discipline cross-checks. One form of cross-check is repetition across time. If the rim went quiet once and stays quiet in repeated observations under different conditions, that leans away from a single night telluric fluctuation and towards something persistent, either in the planet or in the systematic biases of the method. If it comes and goes with weather-like changes on Earth, the suspicion shifts. Another cross-check is independence. different reduction pipelines, different ways of modeling tellurics, different assumptions and the same basic outcome. When the result survives multiple ways of trying to break it, confidence rises slowly. But there's an especially sharp test implied by the outline, and it's worth lingering on because it's so tangible. Telluric absorption lines occupy specific wavelength regions more heavily than others. If a planetary feature goes quiet, primarily where telluric bands are strongest, that's a warning sign. It doesn't prove telluric contamination caused the quiet, but it tells you where to look for the fingerprints of Earth. And then there's a quieter confounder, one that doesn't come from Earth's air or the detector, but from our own models of molecules. Line misidentification and incomplete line lists can turn correction into overcorrection, especially when the planet's expected patterns overlap telluric patterns. If you don't know every absorption line as well as you think you do, you can erase real structure while trying to remove false structure. You can clean the spectrum until it's sterile. In a case like went quiet, that matters. Because the simplest interpretation of quiet is absence. But in spectroscopy, absence can be manufactured. A flat spectrum can be the truth, or it can be what's left after we sanded away the evidence. This is why we keep the honesty tags close to the surface. We can measure spectra in and out of the event. We know Earth's atmosphere imprints variable absorption. We can model and correct, but imperfections can mimic disappearance. Independent pipelines and repeat observations are how we test robustness. And hovering over every step is the title's promise. The rim on HD 189733b went quiet, and the question is whether the quiet is planetary or procedural. So at the end of how we know, we don't get a neat answer. We get something more valuable, a set of competing explanations and a method for putting them in conflict. If the quiet rim is real, it must survive telluric correction. It must survive alternative reductions. It must survive the suspicion that we erased what we wanted to see. If the quiet rim is not real, if it is telluric contamination, then it should betray itself by correlating with observing conditions and by living in the wavelengths where Earth's atmosphere is loudest. And that's the pivot into the next section. Because now the story stops treating Earth's atmosphere as background and starts treating it as a character. We widen the frame. We stop imagining the alien sky alone. We admit the uncomfortable truth. The alien sky is not the only sky in the data. So we change perspective and ask what happens to exoplanet atmosphere claims when Earth instruments and model assumptions are allowed to compete with the planet for the same piece of evidence. The star and planet stay the same. The light still falls onto the detector. The spectrum still looks like a spectrum. But something shifts in the way we see the problem. We stop pretending the exoplanet is the only atmosphere in the scene. On screen, two translucent layers slide over the same band of starlight. One is the atmosphere of HD 189733b, what we want. The other is Earth's air, what we can't escape. And in the overlap, the mystery lives. This is the change of perspective. The outline demands the observer's world becomes part of the evidence, not just the stage. Because the title isn't simply "We saw something." The title is Eclipse Rim on HD 189733. B went quiet, telluric contamination, the full story. That's a claim about what happened and a warning about why it might not mean what it seems. The credibility frame is built into the hook. If a signal can go quiet at the rim, we have to ask whether the quiet belongs to the exoplanet atmosphere or to our own. Here is the tension pair in plain language: planet atmosphere versus contamination. Signal versus artifact. And now we lean into it. Telluric contamination can do more than add noise. It can write patterns into the spectrum that look like chemistry. It can also erase patterns by forcing our correction algorithms to overreach. Earth's atmospheric imprint varies in time, and those variations can line up in ways that mimic in-event versus out-of-event differences. So the question becomes, if the rim on HD 189733b went quiet, does that quiet track the planet, or does it track the conditions under which we observed? This is where the story tightens, because we can't feel the answer. We have to test it. One test is brutally simple. In spirit, does the quietness align with Telluric heavy wavelength regions if the disappearance is strongest, exactly where Earth's absorption is most volatile? Suspicion rises, not certainty. Suspicion. In spectroscopy, location matters. A feature that fades where tellurics are loud is not automatically false, but it carries a heavier burden of proof. But the outline makes clear that tellurics aren't the only alternative explanation we have to entertain. Even if we could eliminate Earth's contamination perfectly, the spectrum still isn't a direct photograph of the exoplanet atmosphere. It's an interpretation filtered through models, through retrieval. Retrieval is where we turn a spectrum into a story about gases, clouds, and temperature structure. It is also where the story can be quietly steered by assumptions. Retrieval priors. Assumptions about temperature profiles, chemistry, and cloud properties can pull a weak spectrum toward flat solutions. If the data at the rim are marginal, the retrieval may prefer a muted atmosphere, even if the true atmosphere is more structured. A rim that went quiet can be in part a rim that our model learned to distrust. This is the second tension pair. Model fit versus uncertainty. Detection versus interpretation. And then comes the confounder that can impersonate almost anything, clouds and hazes. A haze doesn't have to be dramatic to be decisive. A thin veil high in the atmosphere can smooth out spectral features across multiple wavelengths. It can make different gas combinations look similar. It can turn a planet with rich chemistry into a planet with a nearly featureless signature, especially at the rim where the path length and geometry are already pushing us towards subtlety. Clouds/hazes degeneracy means that a muted feature can be explained by many different underlying realities. The atmosphere may still contain the gases we're looking for, but hidden behind scattering particles that flatten the spectrum. In other words, went quiet does not automatically mean nothing is there. That matters for the bigger stakes of this series, because the micro-niche here, exoplanet atmospheres as evidence, feeds the search for signs of life. And the life detection trap is always the same shape. A pattern that seems meaningful can be manufactured by the interplay of contamination systematics and model assumptions. This case is not about a biosignature on HD 189733b. It's about how we learn to be careful before we ever claim one on a temperate world. The most seductive explanation for went quiet is the one that assigns agency to the planet, time variability, a change in the atmosphere itself. Weather, winds, condensation, heat redistribution. We allow that possibility, but we don't get to privilege it. The outline is strict time variability is plausible, but it is also easy to hallucinate when sampling is thin. If we only have a few eclipses or transits, apparent changes can come from sampling windows, what nights we observed, what conditions prevailed, what portions of the event were captured cleanly. A rim is brief. Miss a portion. Misestimate a baseline. And you can create a story of variability without a variable planet. That's the confounder we have to name plainly here. Time variability versus sampling. Baseline length. Windowing. The danger of thinking we've watched the same event multiple times when in practical measurement terms, we haven't. So this section becomes a kind of courtroom and the spectrum is the witness. We let multiple explanations cross-examine the same evidence. Telluric contamination did Earth's atmosphere change in a way that made the rim appear quiet. It can. Instrument systematics did the measurement drift subtly at the worst possible moment. We'll name that more fully later, but it looms here as a competing cause. Retrieval assumptions did our models prefer flatness because the data were weak at the rim? They can. Clouds/hazes did degeneracy. Could the atmosphere itself be masking features without changing chemistry? Yes. True planetary variability. Could the limb genuinely differ from one event to the next? Possible, but not yet earned. And now, after the perspective shift, the mystery feels different. Less like a single vanishing clue, more like a lesson about how exoplanet atmosphere claims survive. The title's phrase, "the full story," is no longer a promise of a dramatic reveal. It's a promise of a conservative conclusion, one that survives the strongest alternative explanations, which means the next move is unavoidable. We stop living in possibilities and assemble what remains after the gauntlet. We build a best current conclusion that respects uncertainty without hiding behind it. So we narrow the frame again. We take HD 189733b, the rim that went quiet, and everything that could have silenced it, and we ask what in the end we can responsibly say. The spectrum returns, but this time it's layered with caution. Not as decoration, as structure. 3 steps stacked like a spine, what was observed, what was corrected, what was interpreted. And at the far right edge of the plot, where the eclipse rim lives, the uncertainty bars widen as if the data itself is admitting where it's weakest. This is the cosmic checkpoint. Not a victory lap, a moment to decide what survived. HD 189733b is still there. The exoplanet still passes in front of its star, still creates the geometry that lets us probe an atmosphere. But the story we tell about that atmosphere has to pass through a narrow gate: repeatability, calibration, discipline, and the willingness to say we don't know yet when the evidence demands it. The title threads through this like a quiet oath. Eclipse rim on HD 189733b went quiet. Telluric contamination, the full story. The phrase "went quiet" is a claim about behavior. The phrase "Telluric contamination" is a claim about vulnerability. The full story has to hold both without choosing the more exciting one. So what can we say honestly at this checkpoint? First, we pin down what is not in dispute. HD 189733b has an atmosphere. That is not the question. The question is, which features in the spectrum are robust, and what it means when a rim phase signal appears muted when it seems to go quiet. And then we confront the most important method truth of the episodes. The rim is where we should be least romantic and most skeptical. The rim is a sliver, a brief slice of time, a thin path through an atmosphere. And in that thinness, the difference between planetary physics and processing artifact can be smaller than a human intuition wants to tolerate. So the best current conclusion must be conservative by design. The outline gives us the shape of that conclusion. It doesn't let us name a specific molecule, a specific line, a specific detection claim. It forces us to stay at the right altitude explanation categories, not headline chemistry. Here is the checkpoint, stated with discipline, The quiet rim on HD 189733b is most consistently explained by a mix of telluric contamination sensitivity and muted spectral contrast, often associated with clouds or hazes, rather than a single dramatic chemical disappearance. That sentence is doing a lot of work. It doesn't say the planet didn't change. It says we do not need true planetary change to explain the quietness. It says the quietness lives in the intersection of measurement vulnerability and atmospheric muting mechanisms. And now we tighten it further by asking what would shift the burden of proof. One of the clearest tests is where in wavelength space the quietness shows up. If the feature vanishes preferentially in regions that overlap strong telluric absorption bands, the burden shifts toward the limits of Earth atmosphere correction rather than toward a physical change in the exoplanet atmosphere. That's not cynicism. It's method. It's the rule that keeps false positives from becoming folklore, because a null result, an apparent flattening a missing feature, can be real. Or it can be manufactured by calibration choices and environmental variability. In exoplanet spectroscopy, absence is not automatically evidence. It's an outcome that must be stress-tested. This is where we keep the tension pair, explicit signal versus artifact, detection versus interpretation, planet atmosphere versus contamination. Now we bring in the other confounder that always hovers, just off camera, instrument systematics. Even if telluric contamination is modeled well, the instrument can still drift in subtle ways. Wavelength calibration shifts detector behavior, thermal stability issues. The outline requires us to name this specifically here, even if we don't dive into the engineering. So we say it plainly. A rim phase signal is delicate enough that instrument systematics can mimic a change or erase a real one without announcing themselves. That's why best current conclusion is not built on a single pipeline, a single night, or a single interpretation. It is built on what persists when we try to break it. And what persists at this checkpoint is not a dramatic claim. It's a disciplined posture. The planet's atmosphere exists and is measurable in principle through spectroscopy. The rim going quiet is more naturally explained by correction sensitivity and muted contrast than by a definitive chemical vanishing act. True atmospheric variability remains possible, but it requires a higher standard repeatable changes across instruments and broader wavelength coverage that reduce telluric vulnerability. That last part is the quiet edge of awe in this series. Not that we have certainty, that we know how to earn it. Because this checkpoint is not only about HD 189733b, it's a calibration for everything that comes next in the search for life. If a hot Jupiter bright observed often, and in many ways easy, can present us with a rim that went quiet, then what happens when we chase subtler signals on smaller, cooler worlds? Signals we might one day want to call biosignatures, or more delicately still techno-signatures that would appear as faint, unusual atmospheric patterns. At this moment, we do not speculate beyond the outline. We simply state the implication. The discipline we practice here against telluric contamination, against instrument systematics, against the seduction of a neat story is the same discipline that will decide whether future claims about signs of life are credible. So the cosmic checkpoint closes like this: the case of HD 189733b teaches us that the most dramatic moment in the data, the moment it went quiet, may be less a message from the planet than a mirror held up to our methods. And with that, the narrative turns toward meaning. Not big metaphysics, practical meaning. What this kind of quiet rim teaches us about the life detection trap, about biosignature claims. versus false positives about techno-signature ideas under observational constraints. We take one last look at the rim-thin, uncertain, hauntingly precise, and we step into the limitation-heavy reckoning that comes next. The final image is almost too simple. A dark planet, a bright star, and a rim that for a moment seems to exist, then fades back into the noise. It's not the universe turning away. It's the measurement showing its seams. We stay with that seam because the ending of this episode can't be a triumph. The outline won't allow it, and the science shouldn't either. This is the limitation-heavy section. The place where we look directly at how easy it is to be fooled, especially when what we want is not just an exoplanet atmosphere, but meaning. The search for signs of life. The hope that chemistry can become a message. And the title remains, our anchor and our warning. Eclipse rim on HD 189733b went quiet. Telluric contamination, the full story. If a signal can go quiet on a loud, well-studied, hot Jupiter, then any future biosignature-like pattern on a quieter, smaller world must be treated with even more caution. That's not pessimism. That's respect for false positives. So we name the core tension pair again, and we let it sharpen. Biosignature claim versus false positives. Detection versus interpretation. HD 189733b is not in the habitable zone, and we're not pretending it is. But it teaches the lesson we will need when we do stare at habitable zone atmospheres. The data do not come labeled life or not life. The data come as tiny spectral differences extracted through calibration, filtered through retrieval, and vulnerable to contamination. In other words, the life detection trap is methodological before it is philosophical. Here is what we can say with the firmness the outline permits. Biosignature claims any claim about signs of life in an exoplanet atmosphere cannot rest on a single fragile feature. They require multiple lines of evidence across wavelengths and repeated observations. That's not a preference, it's a necessity born from how spectroscopy behaves in the real world. Why? Because we just watched a case where went quiet could be explained without invoking a dramatic planetary event. A vanishing or appearing feature can be created by the observer's atmosphere by subtle systematics. By the way, a model prefers one explanation over another when the data are weak. If that's true on HD 189733b, it will be true often more so on smaller, cooler planets where signals are fainter. So we lay down the safety rails that make future discoveries believable. The safest pathway is redundancy. Different instruments, different epochs, different observational channels when possible. Transmission constraints versus emission constraints, not to inflate the story, but to see whether the story is stable. The goal is not to detect at any cost. The goal is to ensure the detection is not a false positive, and we bring the role of retrieval into the light without turning it into a lecture. Retrieval choices can move the conclusion. Cloud models, temperature profiles, chemical assumptions, these are not mere technicalities. They are part of the result. That means robustness checks are not optional. They are the difference between inference and illusion. This is where we make one brief calibration to Earth, no more than the rules allow. Earth's atmosphere is rich enough that if you took only one narrow slice of it under changing conditions, you could misread it. That's the point. Not that Earth is the target, but that partial contaminated views can mislead even when the truth is known. Then we return immediately to the exoplanet case, because that's where the meaning lives. The rim on HD 189733b went quiet, and the full story is not a single villain. It's a network of vulnerabilities that can conspire. Contamination, telluric absorption that changes through the night. Instrument systematics, subtle drift that can reshape a weak signal. Model assumptions priors that can prefer flatness when the rim is faint. Clouds and hazes, real atmospheric physics that can mute features without changing chemistry. And now carefully we touch techno-signatures only within the outline's constraints. If we ever claim a techno-signature through an exoplanet observational channel, an unusual atmospheric industrial gas pattern, or some spectral anomaly tied to transit or spectroscopy, it would face the same gauntlet. First, Telluric contamination systematics and model dependence. The bar would be higher, not lower, because the consequences of being wrong would be larger. So the honest emotional beat here is not "we are close." It's "we are learning what it takes to be sure." This is where we deliver the named unknown, as the outline requires measurable concrete and resolvable with future data. The unknown is this telluric correction residuals versus the true planetary spectral amplitude at the eclipse rim. In plain language, did the rim on HD 189733b truly go quiet, or did our attempt to remove Earth's imprint quiet it for us? That unknown has a shape. It can be tested. Future observations that emphasize telluric quiet wavelength regions. Broader wavelength coverage that lets us compare parts of the spectrum, where Earth is loud to parts, where Earth is quiet. Cross-instrument consistency that doesn't rely on a single pipeline's habits. Injection recovery tests that ask a blunt question: if a real rim feature exists at a certain level, would our methods preserve it or erase it? We don't promise what the answer will be. We promise what the question is. And that's the ending this story earns. Not an announcement, but a disciplined kind of awe that we can look at an exoplanet atmosphere across unimaginable distance and still argue responsibly about what is real. That the argument itself, the insistence on confounders, on uncertainty, on retrieval humility, is how science protects meaning from wishful thinking. The final image returns to the rim. A thin crescent against the star, then a flattening line. Then quietly, Earth's telluric band sliding into place over the same region, a translucent veil revealing the ghost that can erase a world. Sometimes the universe doesn't go silent. Our own sky simply speaks over it, and the most profound discoveries begin the same way, with a signal that refuses to be trusted.